Hi, this is Robert Bolaños. Welcome to the analysis, design, and simulation of a forward converter, part 8. This is going to be on synchronous rectification. It's going to have a lot of information, so hopefully I can explain how it works. Okay, so let me just go ahead and review a little bit what we did last time. I showed the IR2110. I did a simulation or how it worked, and I did a simulation, or at least I showed how I modeled it and then did a simulation, and I did some quick calculations, and this number was kind of out of the air, so to speak. So, and then I said that this was to set up the next discussion, which was synchronous rectification. Okay, so here's a statement that I want to make, that at higher currents and low voltage, less than 5 volts, diodes are not as efficient. Okay, so I kind of calculated that, a quick calculation. Okay, another statement that I can say is that if you replace the diodes with the MOSFET, you can increase efficiency. Okay, normally that's true, but you have to make sure that the power that it takes to drive the MOSFETs does not exceed the power that you're saving from the diode losses. Okay, so that's very important. So we're gonna check on that, maybe on this video or the next video. Okay, and another statement that I want to make is the synchronous is much more complicated. That's for sure. It is much more complicated, and the switching, since you're going to be switching the forward and the catch to MOSFETs, typically the switching has to be very precise. Okay, so let's go back and just review a little bit. We're going to try and calculate the power of the diode. Okay, and there's two diodes. This is called normally the forward, and this is called the catch. And you're typically going to have two states. You're going to have the on state, which is this one. This is one of the states, and where this diode is on, the other one is off, and the second state is the off state, in which the forward is off, but the catch is on. So this is on, and this is off. The forward is off. Well, here, so the other way, this is off. Okay, and the current that you would see typically through the secondary, this one, and let's say it's I secondary, and we'll say that this is I secondary. It's going to look like so. Okay, now in the example that I'm using 10 amps as the average, so you're going to have a swing that goes up and down around the average. Okay, so if you decompose the current of the forward looks like this, and the catch will look like this. Okay, so this is just a little bit of background information. Okay, now typically when we're calculating power losses, you can assume that the voltage across the diode is 0.6 volts. Okay, and since the average output here is going to be 10 volts, you can make a quick calculation and just say that it's 7 watts. Okay, so if you want to get a little bit more accurate, okay, on the previous video, I just said that the voltage drop was 5.5 based on this. I said the voltage is going to be let's say 5.5, and this is kind of like uh, a little bit of hand waving, but let's calculate this a little bit more accurately, basically more accurately. So to do that, we can use the theory or the concept of dynamic resistance. Okay, so to calculate what the voltage across the diode is at a different voltage. Okay, so in this case, we're going to take these two sets of data and these two sets of data, and basically we're going to find out the slope. This is the slope. Okay, so we want to put the delta V in the numerator, and we want to put the delta I in the denominator. Okay, and when you do the calculations, you see that you have a slope of 0.004 ohms. So basically, at a certain 5 amps, you have approximately 0.5 volts, and then way over here, which is 50 amps. Let me change the color. We're going to say that at 50 amps, that you have approximately 0.68. So we're measuring the slope. Okay, and that slope, we're going to call it the R dynamic, or RD. Okay, so now that we have the dynamic resistance, now we can make a little bit more of a more accurate calculation. Okay, instead of doing a little bit of hand waving. Okay, so now the question is, what is the voltage across the diode at 10 amps? Okay, so let's calculate that. We're going to say that it's 0.5 volts. Okay, and now we're going to put a delta. This is a delta current. And remember, we're starting a delta from 5 amps to 10 amps. We want to find out what this voltage is. So, since we have that delta, which is 5 amps, we're going to multiply that times the dynamic resistance, okay, that we already calculate, and that is going to give us approximately, this will give us 20 millivolts. Okay, so let me correct this. So when you calculate it, you should have a voltage of 0.52 volts, and that would be at approximately 10 amps. So this is more of a more accurate estimation. Okay, so now if you know that it's 0.52 volts, multiply times 10 amps, you have approximately 5.2 watts. Okay, so that's a closer calculation. So now let's go ahead and look at SPICE. Okay, and let me go ahead and look at the schematic to show you how I came up with that. You can do a dot. Okay, you can do a dot pound calc, and what we're going to do is, in this case, let me bring this up here so you can see what's happening. So I'm saying that the power of the diode is the average of this voltage, basically the voltage of VSAC and node 4, basically the voltage across these two diodes, these two nodes, times the current flowing through this diode. And then, since this is a negative voltage, it's going to give you a negative. So we're going to put a negative, that way they add up. So this negative 4 volts is this node, okay, times the current through here. So it's a combination of this diode, the forward, and the catch that we're calculating by this statement. Okay, and once I have this statement defined, then all I have to do is tell it to plot it, and here's a plot. Okay, let me go ahead and take that off. Okay, and here's the power. And if we run it a little bit longer, you can see that it goes into acetone, and it's approximately 5.19 watts, which is pretty close to what I calculated. Okay, so this tells me that I'm calculating it correctly, and tells me that it's quite a bit of power. Okay, so now let's go ahead and continue. We've already calculated the power was approximately 5.2. Okay, and then when you plug it in into this equation, we calculated the efficiency is approximately 86%, and this is with a diode. Okay, so we can increase this. We can increase the efficiency by using what is called synchronous rectification. Okay, so what is synchronous rectification and why use it? So that's the question. Okay, well, synchronous rectification is basically, if you look at this schematic, is wherever you have a diode, you replace it with a MOSFET. Okay, why use MOSFETs? Well, MOSFETs have an RDS on. They can be very, very small. They can be as small as anywhere from 1 milliohm to 10 milliohms or higher. But these very low resistance means that you have a much lower power loss. Okay, so that's the mechanism in that you increase. Now the cons is that it's much more complex. Not only do you have to have a MOSFET, you have to have switching circuits that will drive them appropriately. If you don't drive them appropriately, you can have cross conduction through here, through here. So basically you're shorting your secondary. Okay, so that's very critical, and you don't want that. So that's why I'm saying in this statement that the timing is very important, and if it's not done correctly, you will have cross conduction. Well, basically, you can short out your V secondary if both of these are on, whether that one is on or that one is on. Okay, so that's the main idea that I want to say, that it's very important that you get the switching. Very, very good. So now, as far as the pros, efficiency. So that's the main idea, that you want to get efficiency. Okay. So now, let's discuss the various types. I believe there's 2 types of synchronous rectification and a forward. If you notice, this one is very similar. In other words, the diode, the forward diode is on top, so you have a forward MOSFET on top. And if it's on top, typically it's a P channel. Okay. And then you have the catch. And for the catch, you typically will have an N channel. Okay. Now, if you look at this, your source has to be connected here, and your drain has to be connected here, because you want current to flow in this direction. Okay, so that means that this source, that's a problem. see if I can connect this. That node where the source is connected is floating. In other words, this node is going up and down below VCC. And that's a problem, okay? Especially if you're going to connect or try to connect a driver. So basically, this is what you would have to do. You would have to connect a source. This is a source between the gate, okay, and this node, which is very difficult to do, okay? And typically this is not ground. This typically will be floating as well. Will be like that. And then this one, the catch, is not a problem because the source is connected to ground. So this is okay. Okay. So this configuration, at least for the N channel, works very well. Basically, we can connect the driver. The driver can be referenced from, let's say, 10 volts to ground. Okay. And the output can go connected straight into the gate. But you cannot do that with the P channel. Okay. Very difficult. Okay. So there's a solution to this. Okay. And what you want to do is you want to bring, let me expand this a little bit. Zoom out. What you want to do is you want to move the forward, which was here. Okay. You want to move it on the bottom side. Okay. So what does that do? Okay. Well, once you move it to the bottom side, the source is here. Okay. And now instead of using a P channel, you can use a N channel. Okay. So this is equivalent. So now the catch, the source is grounded, and the forward, its source is also grounded. So now it's much easier to implement this design because now you can put a driver that will drive this with no problem. As well, this side you can put a 10 volt to ground. The only stipulation is that they have to be inverted. So one would have to be 100 degrees out of phase, and typically this would be out of phase. Okay. So again, the N channel are better than a P channel as conductors. And the question is why? Why would a N channel be better than the P? Well, the N channels are faster and they carry more current. Okay. And why do they carry more current? Because they're based on electron mobility. In other words, the doping are electrons, and the mass of the electron is much less, so they tend to be much faster. The P, on the other hand, are holes, and they're slower. Okay. But even so, even though this configuration is easier to implement than this, you still have quite a bit of work. Okay. You cannot just connect things together and expect for them to work. So the timing is still an issue. Okay. So the timing is an issue because you want to make sure that you don't have any cross conduction. Basically, you want to make sure that when one is on, let's say this one is on, then the other one is off, and vice versa. And if this is on, then the other one is off. Okay. If both of them are on, then you have cross conduction across this node. Okay. Basically, you're shorting your secondary. Okay. So how do you do that? How do you ensure that you're not going to have cross conduction? Okay. Well, the solution is you make a deadband generator. Okay. Okay. Now, to illustrate what the deadband generator is, here are a little bit more of a system view of the primary. Okay, this is your PWM, and this would be the IR 2110. Okay, so these are the primaries, and whenever the primaries are on, that induces a voltage across the V secondary. Okay, and when the secondary is on, you want this to be on and this one to be off. Okay, so with that being said, okay, this is the timing of the PWM. Okay, so this is off, this is on, and so forth. Okay, now what I want to show here, that when the gate goes on, the primary doesn't go on exactly at the same time. There's a little bit of delay, and that's what I want to show right here. There's a little bit delay, and why? Because there's a delay in the 2110 driver. Okay, so that's the first thing. There's a little delay there. Okay, and then the primary turns on, which is this. We'll say that it's the gate, and the gate also turns on the primary. Okay, now what you want to do is you want to delay the forward a little bit. Okay, you don't want it to turn on at the same time, because what you want to do is you want to make sure that, let me go ahead and see if I can. Okay, doesn't want to change. Okay, I want to see if I can make this a little bit more where you can see this. Okay, okay, let's see if I can explain this. So basically, we're gonna route that signal into a gate transformer, and then from the gate transformer you want a complementary driver. Okay, basically one drives positive, one drives on the opposite section or way. So basically you want this is on, this is on, so this is the forward, and this is the catch. And what I have been saying during this time, that you want a dead band, meaning you want third state. Okay, and I'm drawing this right here. Okay, so this is the dead band where both are off. Okay, and I'm drawing another one right here. Okay, see, that's off here, and here's another dead band. Okay, so basically you want to be sure, see if I can get a different color, that during this time both are off. Okay, so to generate that, a deadband, you need a deadband generator. And basically what I'm showing is the timing of the circuits, of the pulses that we want to generate. Okay, and those two are based off of the PWM. In other words, they have to be controlled by the PWM. Okay, so how do we do that? So now that we have this, see if we can scroll up. Okay, so this is how you implement a deadband. You use two drivers, but then you need a inversion on one of them. Okay, so basically when one is high, the other one will be low. Okay, so now let's look at how the PWM and the forward and the catch work, and how the deadband is generated. Okay, so when this goes up high, transitions high, what you really want is to delay this signal. Okay, so you want a little bit of a delay. When this goes high. Okay, so we'll do that. At the same time, if this is low, that implies that the catch is going to be high, so it's going to come high, but you want it to switch down fast at the same time that the PWM is going up. You want it to go fast. Okay, so I'm going to put fast. Okay, so we'll go up to there, and then when the trailing edge of the PWM hits, you want this edge to go fast. Okay, but then you do not want this signal to go up because this just went down. So you want to delay a little bit. Okay, so you want this edge to be slow. Okay, so by that token you can say that this you want slow as well. Okay, and basically it's going to repeat itself. Okay, and then this you want fast, and you want a delay. Okay, so now let's see if we can bring this up. Let's do the green. Okay. Just bear with me. I think this may be a better way of explaining this. Okay, so now you'll see that this right here, and let me go ahead, during this time the forward is off, but the catch is also off. So basically you have this area where both the catch and the forward are off. Okay, same thing here. Okay, but now you know that during this time there's no way that you can have cross conduction. Okay, but now we know that we need a fast and a slow edge. Okay, so that's the main idea that I want to bring out, that you want this, the leading edge. So basically on the forward you want the leading edge to charge fast. I'm sorry, slow. Okay, and then you want the forward trailing edge to be fast. Okay, so now let's take a look at that. So basically you want the input to look something like this. So you want the leading to go slow, and then you want it fast. Okay, so basically this little delay gives you this delay. So how do you do that? Well, you put a cap, and by putting a cap, when the PWM goes up, it charges through the resistor. Okay, and it may be a high value resistor. It may be 300 ohms, 500 ohms, and so forth. So that creates a slow charging ramp that goes up. Okay, and then when the PWM goes down, you want to discharge this fast. So instead of going through the resistor, it's going to charge through the diode. It will discharge. Okay, so that implements that part. Okay, so now if we look at the catch, see if it'll turn into, okay, so we see that the catch, the trailing, yes, trailing is going to be fast, but then the catch leading will be slow, meaning that you want this to be delayed and this no delay. Okay, and this is the output. So since you have an inversion, then it's going to be the opposite. So now the leading is going to be fast, okay, because of this inversion, right? So that means that trailing will be slow. So you're going to want something that looks like this. Oh no, it's the opposite. So you're going to want something to be fast, and then the trailing to go slow. Fast and slow. Okay, so in that case where you have a fast, you put a diode, and where you have a slow, you put a resistor. Okay, and let's see if that happens. So in this case, if this goes up fast, then most of the current will go through this and it'll charge the capacitor very fast. And then when it hits in the low, when it's low, then the capacitor cannot discharge to the diode, it has to discharge to the resistor, and it'll discharge slow if you make these large. Okay, so that's the trick. Okay, so let me see if I can show a schematic. See if we can open. And bear with me. See if I can find see. I'm looking for a higher radical schematic. And there's actually a chip, the IR1715. Okay, so this is the implementation of this. Let's see if I can. Okay. Instead of using resistors and capacitors, the IR1715 actually uses digital delays, and my version I'm using resistor delays. It's just easier to implement. Okay, and this is my driver. These are the two switches. It's very similar to the 2110 model that I'm using, and the resistance 6 ohms, the off resistance 100 meg ohm, and then the VTs of 5 and 2.5, and then the same hysteresis of 1 volt. Okay, so basically you have a driver here or a gate, and then you have an inverter here, so that makes it complementary. Okay, and here I'm using 100 picofarads, and what I did is I defined the value of this resistor and of this resistor, and I'm saying that it's delay top and delay bottom. So by adjusting this resistor, I can adjust the resistance of this path. Okay, whether it charges slow or discharges fast, and vice versa. In this case, I'm using 2 resistors or 2 diodes. Okay, I can eliminate these diodes if I wish, but I went ahead and left them out on. Okay, just if I need some more, when I play with both edges, then I can put a resistor on this way, on both lines. But this is my implementation of the deadband. Okay, so then let me see if I can find schematic of one that we can run. Okay, and I believe this is it. Okay, so here is my driver, and I label it as IR1715. Okay, and it's getting its input from gate, and gate is the output of the PWM. Okay, and then the output for the forward goes through these 2 buffers. Okay, and goes through these resistors, and it's labeled F for forward. And then the low or the catch goes through these, and then these two labels, F, which is forward, and this is catch, and then goes up to these two MOSFETs, which is labeled F for forward. Here's the gate source, and this is the catch, C for catch. Okay, so we're going to go ahead, let it run, and I'm not going to let it run too long because it'll take a long time, or maybe I will and just edit the simulation time. Okay, let's do a quick preview. Okay, and let's take a look here. Okay, and let me go ahead and take the VSEC off so we can see that a little bit more clearly. Okay, cut. Okay, and let me take the bot off, or actually the bot is the gate, okay, or the PWM. And if you notice right here, this is the catch. Let me go ahead and take it off. Okay, and let me turn this into black and white so we can see it. Okay, and let's see, go ahead and take the other ones off. This one. Okay, so now you can see that there's a little gap in between. So this is the dead band. Okay, now this doesn't, there's a little bit of still a little bit of cross conduction, but because this doesn't discharge as fast, because the capacitors, or actually the MOSFETs, are huge, and I'm going to go ahead and cover that in the next video, but I want to make sure that that you see that. Okay, so that's enough, but there is no free lunch. It does cut down on the power dissipation that you would have used with a diode, but there are other power dissipation that you have to make sure are not exceeded, and that'll be the next topic for the next video. Thank you for watching. If you like the video, please subscribe and give me a thumbs up and share. Thank you for watching.